Hi everyone, thank you for joining this QuantMinds webinar, Neural Networks with Asymptotics-controlled. I'm Lily, I manage digital content for QuantMinds. Before I hand over to Alexandre, I would like to share with you how you could make the most of this webinar, i.e. how you could submit questions to us. If you hover over your toolbar, you will see a little icon that looks like a speech bubble. When you click on that, you will get the option to submit your questions on the side of your screen. I would like to encourage all of you to submit your questions throughout the webinar at any point, and we will address as many of them as possible at the end of the presentation. If you know of people who couldn't make it to the live event, this webinar will be available on demand this Friday in our upcoming e-magazine. So please feel free to share with your colleagues and your peers. I would also like to give a shout out to our social media sites. Give us a shout if you're here on LinkedIn, on the QuantMinds page, and on Twitter @QuantMinds. Now, I'd like to welcome Alexandre Antonov, Chief Analyst at Danske Bank. Alexandre, the floor is yours.
Thank you very much. Good morning or good afternoon, ladies and gentlemen, depending on where you join us from. This presentation is devoted to an attempt to control a neural network from the asymptotic point of view. This is a joint work with Michael Konnikov and Vladimir Peterbach. Now, the goal of this presentation is the following. Machine learning, which will be abbreviated as ML or deep learning, and other neural networks, becoming a standard piece of kit of a bank or another organization. These neural networks can be proposed to speed up slow function calculations. So we tabulate a function using this neural network, and then we can calculate it in a fast manner. And the second is calculate conditional expectations. So you can see a reference mentioned in this presentation. Or they can have another set of different applications. Again, you can check it. You can take a look at this list of references in this presentation, at the end of the presentation. However, the learning points which we try to match the function are concentrated in the main body of the distribution and not in its tail. So a typical neural network fitted to observation extrapolates outside the learning clouds in a completely uncontrolled manner. So we don't know how linear extrapolation or whatever. So we don't know anything in a typical neural network. How does this extrapolation, how it goes out of the bulb? So our goal of this presentation is to incorporate extra information which we have, asymptotics, into this neural network construction in order to control the extrapolation. Many important reasons, such as stress testing of financial model explainability and so on, underlies this goal. Just a quick remark about neural network. So NN is a multidimensional function parameterization. So it consists of different so-called layers. So we have each line constitutes a layer. So first we start with a multidimensional X. We apply a linear transformation to this X having some weight matrix W1 and so-called bias having denoted as B1. Then by an element-wise procedure, we applied a nonlinear function, which is sigma here. This function is called activation function. In different neural networks, they can be different. We can be so-called sigmoids. They can be tangents. They can be squares, for example. A lot of function can be used. Then we have a result coming out of this layer, which is x1. So then we set it to the iterative procedure. To the second layer, we apply a matrix W2. We add a bias vector B. And again, element-wise, we apply the function, not in a function sigma, which can be different from the first letter, for example. So I have the whole freedom. And so the resulting function, f of theta, will be, for example, at the very end, will be linear combination of the x of wn minus 1 multiplied by some vector wn. So, or some matrix. So it can be, the output can be either function or vector functions. So the adjustable parameters, again, are very flexible. So it can be both weight matrices wi, all of them or some of them. It can be also biases and so on. So we can fix some of them and we can adjust the other part of them. So such a presentation is some parameterization actually of the function f of theta. So this theta is a collection of all adjustable parameters over the layers. So it can be, again, it can be everything, it can be just partially defined. The parameters theta are determined from by the so-called learning process. So, or in our old speak, it is nonlinear optimization. As input, we have input points. So the multi-dimensional point x with the subscript p and the result y. So the little p goes from 1 to big P. And so-called loss function, for example, the simplest loss function can be just least squared, summed over all the points. And we play with the parameters, optimizable parameters theta star to get this L of theta minimum. So easy thing. However, this play is done by non-linear optimization, which is performed numerically. So this is, in a nutshell, the construction of this neural forward feed neural network. Then this NN parameterization is numerically attractive. So its derivatives necessary for the optimization can be rapidly calculated by so-called backwards propagation in the slang of neural networks of the data scientist, or in AD in quant language. The resulting function, where we put theta star as optimized parameter, actually approximates the conditional expectation of our input y over x over parameters x. If the points were a result of some small function f, then the neural network approximates the function itself, f. So this trivial case of conditional expectation, which is the same, the same function. Advantages and drawbacks. So advantages is that neural networks are highly efficient and customizable. We can have free parameters control. We can fix them. We can make them the other parameters adjustable, calibratable. We can have bespoke layers. We can have GPU acceleration, put them on the cloud, and so on. And all this can be found in free softwares like Keras, Python, TensorFlow, and so on. So everyone can spend 1 week to write this neural network from scratch. So you just apply it directly. The second advantage is universality of the approximation. So if we fix number of layers, if we fix activation functions, we can come. There is a big probability that we will, which we can describe, tabulate in this way. Well, arbitrary, maybe not arbitrary, but relatively good input function. Also, we have a theoretical guarantee of convergence given sufficient data. Again, we don't know how many data we need, but there is a belief that increasing the data points, training points, we can come up to a good approximation of the initial function. All is good. However, there are drawbacks. For example, numerically solving nonlinear, highly multidimensional problems and unstable. So we can put to local minima. We can do the overfitting and so on. and of course there is a big noise, right? So if we change a little bit parameters, no guarantee that we will return to the same result. If we want to calculate the derivatives of the function, again, if we do it by bump and reprise, then again we can have a big noise and so on. The second thing is there is no asymptotics, so no extrapolation control in standard neural networks. This is our main focus, so we'll describe how it goes. Also, there is no interpolation control in standard neural networks, especially if they are deep multi-layer one. So we can, of course, fit we can nicely fit the points which were learned, but what happened in between, we don't know. So it can have big holes and or big spikes, for example. So this is the neural network is still a sort of a black box. So description of it is filling and description of it given the parameters W and B's is not trivial. So here we would like to at least to try to control the extrapolation, try to control the asymptotics. The theoretical basis of the neural network construction is two sort of theorems. So one of them is Sebenko and Hornig. It underlies the one so-called one-layer network, and the second one is Kolmogorov-Arnaud. It underlies multi-dimensional neural network, multi-layer. So in our SSRN paper, we show that information about the asymptotics is not extractable from the above theorems. So taking a look at these theorems, we can see that actually asymptotics somehow disappear. So it's quite difficult, even from this theorem, from this theoretical basis for the neural network, to get the asymptotics. So you can have a big appendix which is devoted especially for Kolmogorov-Arnaud theorem. We worked a little bit on its simplification of its proof without, of course, giving up important details. So you can check it. It's quite funny, well, a bit complicated, but still, this theorem is one of the bases for neural networks. Right. So the plan of our asymptotic control is very simple. The implementation and of course, the realization is less. So we start with the function f of x, which we would like to approximate with its asymptotics. Of course, we should know the asymptotics. So the first step is to find a console varied function such that it has the same asymptotics as the function itself, either in all direction or partially. Sometimes in some directions we don't know the asymptotics, so we can do it partially only. As the first technical achievement of this presentation is that we have a multi-dimensional spline f as x with given asymptotics. So this is a universal console varied function which has the same asymptotics as the initial function f of x. In the main body, there can be certain deviations. And so this deviation, the rest, so the residual function s minus f of x, will fit with a specially constructed neural network having vanishing zero asymptotics. So we'll discuss how we construct it and so on. So let's first start with this multi-dimensional splines and try to understand how can we attach the asymptotics to that. So first, let us start with the one-dimensional spline. So spline, a cubic spline S of x, is a piecewise cubic polynomial between the nodes hi. So we have a cubic function between which lives for x between hi and hi plus 1. The values derivatives and the second derivatives are supposed to be the same. So when we cross one of the nodes, so we will keep the same values, derivatives and second derivatives. So these conditions are almost sufficient to identify the function, given the values of the function at the nodes. So we suppose that sh of hi is known. So this is known. But we need two more extra conditions to finish the job. So actually, for classic splines, the classic spline has 0 second derivatives at the boundaries. So a classic spline has a flat has a linear extrapolation. So let's see how it looks like. So this is the Black-Scholes price. We're working in finance, so Troy function is Black-Scholes. So this orange one is exact Black-Scholes price. The star here, the spline nodes, the green stars. So the spline passed through these nodes. And however, we have as far as asymptotics are linear, the spline goes out of this learned zone linearly. So of course, we don't know what will happen after that. So spline goes in this smooth direction, goes out of that, and of course, it doesn't fit the whole line, which out of it. Just simply no information about it. Right. So how can we add the asymptotic control to one-dimensional splines? Yeah, actually, it's not that complicated. So we should fix the 2 points, h0 and hn+1. This is the points from which we know the asymptotics. Quite often we have them analytically, and or in other rapid way. For example, for our Black-Scholes, both asymptotics were linear. So we suppose that for x less than h0, the function is f minus, so some analytical functions, namely 0, f at x equals to 0. And for h more than hn+1, it will be x minus k. So very easy, a log of x, so exponential of x minus k. So very easy. So the recipe is simple. We just add the points to the spline nodes. Then we force the spline to pass through them, and we also fix the derivatives. So this has 2 extra conditions, which should have this freedom. So this procedure, of course, doesn't guarantee the second derivative fit. So only the first derivative fits. However, according to our experiments, it's quite useful to have this continuous function even in the second derivatives. So for this, we can pick up the point in between h0 and h, sort of slang notation h1/2, and then we can play with this value such that the second derivative at h0 will be fit. So the same is valid, of course, for the right tail. According to our experiment, the second derivative control helps approximate reasonable functions. So you can see more details in our presentation, but just for now, we'll see that we have it. We can fix also the second derivatives. Couple of graphs. So this is a graph where we have modified our spline to obey the asymptotics. So this point 2 and -2, this is h0 and hn+1. And from here, we add the asymptotics. So we're sure that it will be like our function. In between the asymptotics, there is a line, so this is a cubic spline, this one, such that it fits the asymptotics very well. So we see that the overall fit is very good. Of course, it depends on the function. If the initial function were like this in the middle, of course, there's no guarantee. However, for the smooth functions, we have such a property that fixing 2 asymptotics help us quite a lot to fix the whole function. In general, if we work with the with the quant world, we work with the function as a result of conditional expectation of diffusion. So mostly all of them are smooth. So we can actually say for the certain class of smoothness of function, this fit can be very, very helpful. So what happens in multidimensional splines? Well, we use the tensor product of one-dimensional splines with asymptotic control in each direction where they're available. You can follow the details in our supporting paper, but just to demonstrate the asymptotic control effect, we use again the Black-Scholes price as a function of a spot and the volatility for t equals 1 and strike equal to 100 in the log scale for both volatility and the spot. So see, so this is a Black-Scholes price as a two-dimensional graph. So I have log spot, log vol, and so the function goes up like this, as we know. And so this is the true surface. And then actually we can calculate this spline with asymptotic control. So we fit two-dimensional grid. So spline, two-dimensional splines would pass four-dimensional grid. So these blue dots, and then red dots. This is where the asymptotic control starts. So I have the bulk, and we have the asymptotic control. So we see that it fits the Black-Scholes pretty nice. We can check the errors. So you see the scale of this function is quite several hundred. We see it's quite big. Errors can be written like this, and again the scale is pretty small, much smaller than several hundred, so like 4. And again, this is out of the territory where we have fixed it. So it is outside the bulk of the spline and inside the asymptotic area. So this is so-called no man's land area where there is no control, but only hope that our smooth extrapolation will do it best. If we go with a spline without control, we have something like that. So it will be a different situation, and the errors can be much bigger. So you see this is error with the Black-Scholes and the spline without asymptotic control. So biggest errors, of course, will start out of the zone of the learning, and they can be huge. For example, if we go out and to see what happens slightly outside, we can even sink up to several hundred. So you see, it's quite efficient way to fit the function itself, which is, of course, not surprising. We just use the more information about the function. Right, so now we say, okay, we will calculate a multidimensional spline which has which fits asymptotics, and we would like to calculate a residue. So we take the initial function, we subtract this spline, and we have a residue with a 0 asymptotics in all direction or partially. So we would like to have a neural network such that it has 0 asymptotics or not. So, for example, one of the ways to do that, of course, there are a lot of ways to calculate to get such a neural network, but according to our experiments, this one is one of the best. So we'll propose to parameterize our function as a linear combination with coefficients lambda of so-called Gaussian bells. So this g of x, this is a Gaussian bell depending on argument x with a parameter c and w. So ci is a center, w is a weight, such that this Gaussian bell will be simply exponential of this Gaussian combination of with the center c and the variance w. So if we put larger w, we have the larger bell, and c controls the center. So numerical solver changes the parameters. So this is a c and w. This is a function which are calibratable. Change the parameters and put these Gaussian bells with different amplitudes to fit the function. So in our experiments, we have used w, which is diagonal, so we don't need such many degrees of freedom actually after all. Right. So so this is easy and pretty easy neural network. We have written it, by the way, using the sort of bespoke layer possibilities in Keras. We can overload this layer function, and so yeah, and just simply weighted combination of Gaussian bells with different centers and widths. So of course we should not let the bells have arbitrary centers and widths. So we do not like these bells to go out far. In order to guarantee 0 asymptotics with a specific boundary, we need to restrict them. So the first idea is in a spirit of data scientists, have a custom loss function which penalizes the bells which get out closer to the asymptotic bounds. However, it doesn't work very well. We used, experimentally, it's much better to just to limit the bells, centers and widths where we would like to have them. So the bells will be in the learning zone whenever the widths can touch the asymptotic zone. You can see more details in our paper, but it appears to be quite efficient. Few hundred of these bells is sufficient to achieve excellent precision of our test. So we'll see slightly later how it will work in multi-dimensions. And again, a big part of this presentation is numerical experiments. You can find the Black-Scholes function, again, the simplest, the simple toy example as Paul described in details in the paper. And here we'll present more complicated four-dimensional Saber model described here below. So for tests, we do the kind of normalized Saber model. So S will start as the spot will start from 1, volatility will start from 1. So we'll have some gamma, which is vol. V is sort of ATM volatility. B is skew, and so we have a correlation between these two functions, which we set to 0 in order to get an analytical answer. Because of course we can learn the result of the simulation, but of course it will take definitely much more time. And if we go very far in spot or in a strike, we cannot guarantee that all is good unless we use a crazy number of paths. Yeah, so we decided to put this analytical function for 0 correlation. Nevertheless, fixing the t equals to 1, we have a four-dimensional function of the volatility, of the ATM volatility, skew beta, vol gamma, and strike k. So again, all the details can be found in our paper. So the parameters. To demonstrate the flexibility of our approach, we control asymptotic in some but not all directions. We perform 2 experiments. So first, we control asymptotics in the dimensions of the money volatility V and the strike K, only 2. So we let the neural network extrapolate in B and gamma. So here we do not limit our Gaussian bells, they can go far. Second, we control asymptotics in dimensions of V volatility V, K and gamma, and B is out of control. So 2 and 3. And so we'll see how the precision will change. In order to normalize, to put all these parameters which have different scales in the real Saber to standard span of sort of Gaussian map, we modify them, map them to Z1, Z2, Z3, and Z4. This is sort of normalized parameters, such that they span then leave between like -4 up to 4, -3, like this region. So and we would like to work to work with these ranges of parameters just for our comfort. Just trick here, nothing very scientific. So since all of them are normalized, so they have like a Gaussian flavor, we use the same bounds for all the dimensions. So first, the learning bound LL will be of 1. So the learning zone will be from -1 to 1. Asymptotic bound, where we attach the asymptotics, if any, will be from 1.5. So it defines a region outside where we use the asymptotics. And the measurement bound, it's again bigger bound from -2 to 2, where we measure the performance and errors. So we'll use bounds -1, 1 in 4 dimensions. So for all dimensions with -1, 1 for learning. Then we use -2 for asymptotic control, and -3 is the whole measurement region. So table below shows the corresponding standard and not normalized Tabor parameters. So we'll be in the region from V, like 3% up to 67%, then beta from 0 to almost to 1, gamma from 0.3 to 2, and a strike from 0.5 to 1.6. So quite already, relatively distant regions. Then we have asymptotic bounds for these parameters, so it's slightly wider. You see that, for example, strikes goes up to 3.5, and for measurement even wider. So all the parameters goes almost from 0 up to very large values. So again, more information you can find in our supporting paper. So first step, as we have announced, is that we prepare the asymptotic spline to use it as a consolidate. So first we get a rather sparse grid of -1, 0, and 1 to fix to fit. So we have actually 3 and power 4 points which we're fixing. We don't need here such a big accuracy. We need only to have a control variate, but such an accuracy already know that. So what we do, we subtract from our Saber value, we subtract this asymptotic spline. So it cancels out the asymptotics where we need it, where we impose them, and it has some kind of pillow where we have residue. So outside of this pillow, we have flat asymptotics, for example. We have somebody equal to 0, and inside we have some function, some dependence, which we would like to fit using this constraint radial layer. This is layer which we have built using our Gaussian bell. So we apply the rail to the residue. Testing configuration is the following. So the training set consists of 10,000 points, which we sample again in Gaussian. Each direction is a Gaussian distribution. As we know, as we have converted the initial parameters to this sort of normalized. Of course, to ensure good quality and high sampling granularity, we generate much more points, but we leave only 10,000, which are really inside this region. We reject the others. Then we construct this constraint radial layer, which we use for these desymptotized values. It has approximately 300 nodes, so 300 Gaussian channels with 2,700 parameters. So it's a lot, but not too much. So for controlled dimensions, the centers and widths are within the bounds. For uncontrolled dimensions, we don't say anything about the centers of the Gaussian bells. So we compare our results with the standard neural network, which approximately have the same number of parameters. So we use the standard neural network with 2 hidden sigmoid activation layers, one with 200 nodes and the second one is 4, to ensure the same number, approximately with high precision, the same number of parameters. So very close to our network. According to, again, to our experiment, the sigmoid activation function are very efficient, most efficient for our application. The others actually were not that good. This is another enigma, or just maybe tuning parameters when we have tried different activation function to get the desired accuracy. So again, kind of black boxish behavior. But anyway, so sigmoids were good, and we reached the same accuracy with respect to our initial exercise. So once the approximation to the implied volatility function is learned, we generate a validation sample which covers the larger measurement layer. so we can see what happens in different regions of our experiments. So the errors. Our tests show that controlling asymptotics significantly improves the neural network fit to the cyber implied volatility. Yes, so our output is implied volatility. It's not like the function itself. So the input is mean squared errors. So n against the exact results. We work with the log normal volatilities. So more or less 20% in the bound, but it could go very far on the edges. The learning error is the mean squared error over all the learning points. So what what is reported after the learning is this learning error. We have validation error is the mean square error over all the validation points. We can cut this validation error. We can see it in different regions. So validation error, we can see the points from learning, asymptotics, and measurement regions to see how well the fit is. So we'll see it. We'll see it in one slide. Different type of errors. So here we have a summary of the results for the stable fitting. We have model 1, 2, and 3. Model 1 is the neural network. This is our Gaussian bell neural network where we control the volatility and the strike and the volleyball. So that's the most. This model has the most of the information. Then model 2 has control the volatility and the strike. No development, less control. And model 3, this is our baseline neural network. So no control of the asymptotics at all. So deep NN with 2 hidden layers. So let's check the errors. So the absolute errors, yeah, all the errors are absolute in the implied volatility. So we see that the errors in the learning points are approximately the same, and these errors are. So this is 2 basis points for volatilities, like average volatility of 20%, and much bigger, of course, span if you go to the edges. So quite decent. All of the models has the same order of the errors. Then we go to the validation errors. So when we're done with our loading, we simulate the same number of paths, 10,000, but over the bigger region. So over the whole region, bigger region, we see that the validation error of the model with most of control is much smaller than the model 3, when just standard neural network, and well, 2 times smaller than the model 2. So control of each dimension works quite fine. Then. Having said that, we notice here that the learning region error, so here we use the points only from the learning error, have the same errors, which is in line again with the learning inside these points. However, outside of that, in asymptotics region or measurement region, we have completely different numbers. So asymptotics region, even in fact, if we don't control it, using the asymptotics will improve the accuracy, but by several times. And here, the whole region, of course, we have much less error rather than in the model without any control. So again, let me repeat the observation. All 3 models fit the inputs equally well, were measured at the learning points, and in both learning points themselves and over the validation points in the learning region. Model 1 and 2, of course, overperform significantly outside of the learning region, and model 1 outperforms model 2 outside the learning region, again, because we control a little bit more. Just in the end of the presentation, for further insight, let me show you some pictures. So we visualize the test results in plots below. As far as we work with the 4-dimensional functions, we cannot, of course, see it properly. We will fix 2 arguments and the plot to thrust. So we can find, of course, more plots in our paper. So in this plot, we plot the volatility, it's normalized volatility and the strike, and we fix beta and gamma. So the errors is a function of volatility and strike, where we control the asymptotics. So we see that is for fixed kind of typical beta and typical gamma, we have very nice, very little errors. So here the scale is up to 40 basis points, and again, this is outside of the region where we control the asymptotics. So this is so-called no man's land, where we can see these big, relatively big spikes with respect to the learning error. So learning error is -1, 1, so we can see this triangle here, and asymptotic error is this. So this guy is between the learning error and asymptotics error. So it somehow out of control. The only thing which cannot control. It goes and it goes. If we take a look, of course, at neural network without control, we can have we can see a very big mismatch where the neural network asymptotics, even it's hard to say which kind of asymptotic we have here, but it goes dramatically down. So if you measure something at some point here, you will get a huge error with respect to previous one where the scale was several basis points, and here we have -4, for example. To show the effect of controlling the asymptotics, we will visualize the Gaussian, our Gaussian layer, where we control this strike and vol, but not this Q. So if we have here gamma and strike, so this graph corresponds to errors where we do not control gamma. So you see that outside, so the error when the gamma going to the asymptotic value, it has some strange, we can say, ears. So it goes up like this. However, in the next step, we will see if we control it, if we set it down, we will have sort of pillow. So you see that the same graph, the same thing, but with the control of gamma, on asymptotic control of gamma, we'll have the flat boards like this, because the asymptotics are controlled, and the errors will be will be between this asymptotic with the points where we touch the asymptotics, and between the learning error. So learning error is in the square here, -1, 1. So here, -1/2 where the asymptotic starts, and between them we'll have, yes, a little hills. Again, the scale here is very small, just for example, this one is 1 basis points. So definitely nothing to do with this like 20%. So we'll put all the errors inside, but they're much smaller. Well, so to conclude this presentation, let me just mention you several things which I would like to deliver you. So the first, well, deep neural networks are good in fitting inside the learning area. They're not good in extrapolation. Of course, this has consequences to their usefulness in mathematical finance. So performance in a regime which were not seen before. For example, corona crisis, no one said this, spike for volatilities and so on. So if you trained your model to before corona crisis, and when you start to measure your volatility the 20th of March, you will see that we can completely easily go out of our regime and beyond our result will be complete nonsense, because it will be in the asymptotical with some extrapolation which is out of control and has no sense. Of course, the stress testing is also very important, and the neural network explainability, because it's good to have some tool, but if of course what we can do, we can print our weights and biases and say, okay, say to the say this is our notebook. However, we cannot see, we cannot always we can also try a different direction. We cannot check it. So actually, this is sort of a black box features of the neural network, that we don't know what happens outside of the learning area. So here we propose to make it less black box, to have more control on the especially on the asymptotics of the neural network. So we can the recipe is very simple. We just remove the using a special spline, special universal control variable. We remove the asymptotics and use a layer, bespoke layer of Gaussian kernel functions where we restrict the centers and the widths in order to fit this residual value. And actually, just having said that, using this Gaussian kernel, Gaussian kernels, we also can control interpolation. So if we restrict the minimum width of the bell, we can remove, for example, we can guarantee that inside this little region, we will not have big spikes. For example, if you do not do that, you will have the Gaussian bell can become a little needle, and so you will have we can have sort of spike. But if you fix this minimum value to be kind of reasonable granularity, then you can say that worse than that we will not get anything. So using these Gaussian kernel functions, not only can control, of course, the zero asymptotics, but also can control the interpolation. This again, it's mentioned in our paper necessary, and you have, we give you some results in four-dimensional Saber model, and we have seen that it performs as it should be in theory. Thank you very much. This is all.
Alexandre, thank you so much for this presentation.
Thank you.
I can hear an echo. Okay, great. So I just wanted to remind everybody and encourage everybody to send in your questions. I can see that some of you have already, actually. So that's great stuff. Keep them coming. Alexandre, are you ready for some questions?
Yes. Can I see them, by the way, somehow? Yes. Okay.
Yes. So Constantine would like to know how many Gaussian bell layers did you use in your models, and did you use dropout or regularization layers?
No. So we have used about 300 Gaussian bells, and for both actually Black Scholes and four-dimensional Saber. We didn't use any regularization because, as I said, we physically restrict the lengths and the widths of these layers of these Gaussian bells. So it was much more efficient than regularization, which will penalize going out of the Gaussian bells outside of the learning region. So to limit the width of the Gaussian bells, we used sort of hyperbolical tangent function in order to, again, not stress the solver too much, but has a small dependence of the parameters. So again, the details of this is in the paper. But yeah, 300 layers and physical control on the length without any extra terms to the loss function.
Excellent. Another question came in. What if you add another layer or two to the model 3? How do the learning errors compare then?
Well, we have tried a couple of things like this. Again, keeping the same number of parameters, but we didn't see any difference with this two-layer thing. With two or three, we can say, layer, which we use with the experiments. If we keep the same number of parameters, like around 2000, it is definitely better use two-layer function, which is less black box rather than 3 or more, which we will really don't know what happens. We tried, but didn't add anything with respect to the layers which we have described in the paper.
Here's another question that came in. How do you define overfitting in this domain? Are the asymptotics approximation out of sample or out of sample on the boundaries of the asymptotics?
Well, we didn't do any special effort for the overfitting. The only thing, as I said, we have restricted the bells centers and their width to the conditions, but we didn't do anything. We didn't do any special effort to to minimize derivative, things like this. So it's free, just free. It was free optimization.
All right. Travis would like to know, how do you determine how far out to put your asymptotic points?
Oh, it's a good question. It's a good question, and actually, of course, the first is of course the asymptotic point is available starting from certain strike, for example, certain value of strike. So we cannot put it like a true, I don't know, 3 or something. It should be, for example, 10. So there is a mathematical reason from where we can write an analytical formula for that. So the first, and the second is if we even know this point, it should not be too far. It should be too close to the. It should not be too close to the learning area, because it can make sort of waves in between, in this no man's land, which I have explained, the area between the asymptotic point, the learning point, and the asymptotic point. So if we put them close to each other, they can have sort of waves where the model tries to fit them and it cannot. So they should be relatively, well, relative. Of course, it's experimental, all this experimental, but they should be relatively far from each other, but not too far. So, yeah.
All right. Ted has actually 2 questions. One of which is, did you try to take into account data from MC simulation or exotic instruments?
Actually, no, we didn't try anything about the exotic instruments. However, of course, in the as I said, the Monte Carlo simulation is not always good unless it's specially adapted for when we work for far points. If we have, for example, large spot or large strike and so on, Monte Carlo can give us the quite big number, and also the function itself can be noisy, right, with the Monte Carlo. So we didn't do that. We tried the analytics. However, the Monte Carlo simulation, again, if everything is okay on the edges, if it works correctly, the neural network will maybe just smooth it out a little bit. Will smooth out a little of noise to make sort of conditional expectation. So it shouldn't be a problem. A little noise is acceptable. However, the asymptotics, of course, should be correct. Exotic, we didn't try another. So maybe it's the second step, but for the moment it was just an analytical function for an option price like Sabre.
All right, and Ted's follow-up question is, did you apply neural networks to the problem of hedging portfolios?
No. Well, I know that the Christian I know that this problem can be solved using the neural networks. For example, the works of Bauer and his colleagues. And there are indeed special asymptotics where we construct the hedges. We can say, for example, that delta of this and that option has a certain asymptotics. For example, we know more or less how it goes, and so this can be helpful for this application. The only thing we should know the asymptotics of these positions.
Super. Marcos Cajaira I hope I pronounced your name right, would adding additional weight for the errors at longer maturities, more like effective variance, help?
Yeah, I think so. Yeah, maybe. Yeah, that's a good idea. Yeah.
Short and sweet. In using neural networks for estimating demand functions, the standard problem is the neural network not respecting regularity conditions. If regularity is imposed, you often lose the approximating theorem. Would there be a benefit of imposing structural regularity conditions on the function, perhaps at least at the asymptotic points?
I think yes. Yeah.
Fantastic. And we just got a new question in. Can you suggest resources to learn more about asymptotics?
So to read about more asymptotics?
To learn more about them, yes. I'm guessing reading would be included in that.
But for example, in the Saber asymptotics, we have in our recent book with Michael Koenig and Michael Spector, we have quite a lot about the asymptotics of the Saber model. Then authors like Blanca Horvat also, they devoted a lot to the asymptotics. Or, for example, if you work with if, for example, if the goal here is to calculate a condition expectation or the exposure of a portfolio, it's often quite easy to understand it taking a look at the zero bond price or at the dependence on the option. For example, if in the half-white world we concentrate on the zero bond price, and we know that, for example, the zero bond is exponential of minus some coefficients times rate. So we know that asymptotic here it will be exponential, so it will get down with the rate. If we observe an FX option, again, we know that the asymptotic in terms of FX option will be for large x, will have x minus strike. For Liesel, we'll have 0, for example. So in almost all the cases, using simple arguments and simple considerations, we can get the asymptotics. If you would like to get something more specific, then, for example, if you would like to know what happens before the function goes to x minus k, of course it's possible, but it requires big effort. But again, as example, you can check maybe our book about the Saber, where we have it well explained some techniques how to do that.
Great. One last question, unless more come in. Can your method of control variate help a linear learning like regressions?
Yes, actually, yes. If, for example, if again we subtract using this special spline, if we remove the asymptotics, then we can replace this Gaussian Bell nonlinear network by, for example, spline regression with multidimensional spline regression with zero asymptotics. It is actually in our paper there is a little paragraph corresponding to that. So we don't need anything very fancy. We need only linear regression, and we can, with some success, we can calculate this on the splines with zero asymptotics. So it's not the asymptotic splines where we fix the initial function asymptotics, but more that spline with zero asymptotics. So these guys are linear. So we can construct this basis such that it is sort of Gaussian bells, but with kind of wider coverage. So they're less local, but they fill the kind of earth better. So we don't need them. We don't need several thousand of them, but it's sufficient to have maybe several dozens. But again, in our paper, you can find it.
Fantastic.
Yes.
Fantastic. Yes, you should already have a link to the presentation and a link to the paper as well. So thank you very much for joining us today. If you enjoyed this webinar, please let us know. If you head over to our LinkedIn page named QuantMinds very easily, you can let us know there or on Twitter at QuantMinds. And while you're there, why not follow us for the latest updates on our face-to-face and online events, including webinars like these. So tomorrow at 2 o'clock is our next webinar with Svetlana Borovkova, who will be talking about how COVID-19 has impacted this sector. So that should be an interesting conversation, I think. So until we meet again, stay safe and thank you again.
Thank you very much for your attention and inviting me.